Good morning, dear students. Now we shall take up chapter number 3. In this chapter, we take one-dimensional problems such as axially loaded bars or truss elements and one-dimensional beams. The knowledge of axially loaded bars we also use to solve two-dimensional truss problems. This is what we do in this particular unit number 3. Right? Now, so what we do? We use the total potential energy, stress-strain relations and strain displacement relations for finite element formulation of one-dimensional problems. We all know that for one-dimensional problems we consider only one coordinate because the geometry of the domain, the properties of the materials and other parameters are dependent on only one coordinate x. Right? Now we take axially loaded bars. The axially loaded bars behave as the elements of the truss because truss element is a two-force member. So therefore, the behavior of axially loaded bar of uniform cross section and the behavior of truss element are same. Okay. Now, for one-dimensional problems such as axially loaded bars, the displacement, strain, stress and also loading depend on only one coordinate x. Right? And moreover, the loading such as body force, surface traction and also the concentrated force depend on only one coordinate x. Right? Now, we shall see the displacement. Here the displacement is dependent on only one coordinate x. Only one coordinate x. Displacement is a function of variable x. Now, here stress, it is also a function of variable x. And strain, it is a function of variable x. Traction, it is dependent on variable x. Body force, it is dependent on variable x. For one-dimensional problems, we know that within the limit of proportionality, stress is directly proportional to strain. Hence, the stress sigma which equals to Young's modulus into strain. We know that the displacement is a function of variable x. Therefore, the strain epsilon we can define as du by dx. du by dx. What is sigma? It is the normal stress. What is epsilon? It is the normal strain. Okay. So once you know the strain epsilon, you can determine the stress. Now, when we take the one-dimensional problem such as axially loaded bar of uniform cross section. Look at this diagram. It is an axially loaded bar because it is subjected to a pull P. It is subjected to a pull P. A force P is acting. The tendency of this force is to produce elongation in this bar. Right? Now, we see the cross section of this bar. The cross section of this bar is same everywhere. It is a bar of uniform cross section therefore. Okay. Now, L is the length of the member. This is the reason why, if you consider an infinitesimal element of thickness dx, distant x units from the fixed end, the volume of this differential element, dv equals to a into dx. dv equals to a into dx, because the cross-section area of this member is same throughout its length. It is an axially loaded bar of uniform cross-section. What is variable here? The length. Okay. Therefore, we can define the differential volume of the element of thickness dx equals to a into dx. Okay. Now, here we classify the forces basically as surface force and body force. What are the examples for surface forces? The examples for the surface forces are surface shear, and friction on the surface of the object. Friction, surface friction is the example for surface force, right? And the concentrated forces acting on the surface of the object are also the examples for surface forces. Now let us see. So here I take an object like this. Observe, this member has uniform cross section. Now, this is subjected to a force P. Where it is acting here? On the end face of the member. Therefore, it is the surface force. Next, if the traction is applied on the surface of the member, it is also considered as the surface force. That is the traction, right? And surface friction is also another example for surface force. And what are the examples for body forces? The example for body force is self-weight. Okay. And another example, centrifugal force we can consider as the body force. Okay. Now, we see a one-dimensional bar loaded by several forces. So here, this is the concentrated force acting at this point. And this is the concentrated force acting at this point. Okay? Where they are acting on the surface of the object, on the surface of the one-dimensional body. Therefore, P1 and P2 are the surface forces. Now, if you see, here we observe the traction on the surface of the object. T is the traction. Traction is the surface force. And now, these arrows represent the force distributed on the entire volume of the object. Okay, the force distributed on the entire volume of the object is the body force, that is the weight of this object. Okay, so here we have the concentrated forces acting at several points, the body force, and also the traction. Traction is applied on the surface of the object. I told you the examples for traction. Surface shear is the example for traction. Right? Now, friction, surface friction is the example for traction. Okay. All these are acting vertically downward. Therefore, to consider these forces positive, we have taken here a positive coordinate axis with origin at the fixed end. Hence, we take all these forces, positive because they are acting in the direction of x-axis. Okay. Now, body force. Body force is distributed per unit volume because it is acting on the entire volume of the object. Hence, we can define the body force as the force distributed per unit volume. Right? And coming to traction, traction is the distributed force acting on the surface of the body. Acting on the surface of the body. Therefore, we can consider this traction as the force distributed over the area. Hence, we can consider this traction as the force distributed over the area. Okay. As I said, frictional resistance, viscous drag and surface shear are the examples for surface traction. Now, in one-dimensional problems, if traction is distributed as force per unit length y, that we see now. In one-dimensional problems, traction is considered as force per unit length, that we see now. Now, I take again a bar of uniform cross section. Okay? Uniform cross section. Assume that this has circular section, therefore this is the cross section. Assume that it has circular section. Okay. Let R be the radius of this circle and L is the length of this bar. L is the length of this bar. Okay. Now, on the surface of this member, I consider the traction acting like this. On the surface of this member, I consider the traction acting like this. Now, if you determine the area of the surface on which traction is applied, what is the area? The perimeter of this circle into length of the member. Therefore, what is the surface area? It is 2 pi RL. In this, along the length, 2 pi R is same, it is constant. Perimeter of this member is constant throughout its length. Perimeter of the this bar is constant throughout its length. Hence, we can define, say here, the traction as the force distributed over the length because the perimeter is constant throughout the length of this bar. Understand? That is what I have written here. That is what I have written here. It is defined as the force per unit length. Force per unit length. Understand? Now, we see the finite element modeling. So how you divide the domain? We divide the domain into subdomains. Hence, element division is very, very important along with node numbering. Okay. We take an example here. This is a bar of varying cross section. It is not a bar of uniform cross section. Observe carefully. The cross section of the bar is varying with respect to length. One end is fixed, right? One end is fixed. other end is free. The cross section of this bar is varying. It has variable diameter. Now, how you model this member? How you model this member? For one-dimensional problems, we know that the element connects two nodes. Therefore, if you take a two-noded element, it appears like this. It is a two-noded bar element with uniform cross-section. For finite element modeling, we should consider the elements with the uniform cross-section. For first element, the cross-section should be uniform. For second element, the cross-section may be different, but it should be same. For third element, the cross-section may be different, but the cross-section area should be same throughout its length. Each element must have uniform cross-section because the one-dimensional bar element has uniform cross-section. This is the reason why we can model this bar as the stepped bar like this. As the stepped bar. How do you model here? See here. From here to here, we consider this as one element. We consider this as one element. From here to here, we consider this as one element. This is one element, like this. See here. This is one element. Okay? Now, the cross section of this element in the direction of x should be same. Therefore, I have considered uniform cross section. How we have determined? See here, here, the diameter of this section. Here also you know the diameter of this section. Hence, the cross section area you can calculate here. The cross section area you can calculate here. Understand? Now, you can replace this by an element of uniform cross section taking the average diameter. Understand? Next. This is another element. This is another element. This is second element. How it is looking? It is not having uniform cross section. It is looking like this. Observe carefully. Second element is looking like this. Like this. Understand? Now it is not having uniform cross section. Right? Take the diameter of this section and take the diameter of this section. Then determine average. Hence I can replace this. I can replace this by an element with average diameter. Length I am not changing. Length of this element is same as this. Length of this element is same as this. Okay? Next. If you observe this, how this is looking? Again we see how this is looking. It is looking like this. Right? Here also the cross section is not same in the direction of x. We have the diameter of this section, and we take average. Therefore, this is the average diameter calculated from these two diameters. Hence, element 3 has the uniform cross section. Understand? Now, this is element 4. This element 4, if you see carefully, it is appearing like this again. It has no uniform cross section. How it is modeled? It is modeled as an element of uniform cross section like this. Understand? We have the diameter here. We have the diameter here. Take the average and replace this by an element of uniform cross section. How it is modeled? It is modeled as a stepped bar. Why it is modeled as a stepped bar? Because for one-dimensional problems, right, we consider one-dimensional element like this, which has uniform cross section throughout. Therefore, when you see all these four finite elements, the first element has uniform cross section. The second element has uniform cross section. The third element has uniform cross section. The fourth element also has uniform cross section. Understand? So here, how many elements we have taken? Only four elements. This is fourth element. This is third. This is second. This is first. Instead of taking four elements, if you take 10 elements, or 15 elements, or 20 elements, with increasing number of elements, you get better approximations, you get better results. Understand? Right. Elements are numbered here. Element numbers are encircled here. Element numbers are encircled here. This is the first element. For first element, this is the node 1 and this is the node 2. Right? Node 1 is the first node of first element. Node 2 is the second node of first. Next, node 2 is the first node of second element. Node 3 is the second node of second element. That is how we can understand. Okay, next. We have the finite element model. We have the finite element model. Here, how many elements are there? 4 elements. And how many nodes are there? 5 nodes. Therefore, it is a 5-node, 4-element model. It is a 5-node, 4-element model. Okay, right. Now, each node has 1 degree of freedom, that we know. And in addition to the cross section, traction and body forces are also treated as constant within each element. In addition to the cross section, the traction and body forces are also considered constant within each element. However, the cross-section area, traction and body forces differ in magnitude from element to element. Element to element. Now, if you observe the displacements of the nodes, see here. This is node 1, right? This is node 1. This is node 2. This is node 3. This is node 4. This is node 5. Okay. What this represents? This represents a domain. Entire stepped bar represents a domain. Now, this is finite element 1. This is finite element 2. This is 3. This is 4. Okay. So 4 subdomains are there. In the entire domain are the nodal displacements on the domain represent global displacements. Hence, the displacement of node 1 is the global displacement denoted by Q1. Here we follow a convention. We use capital letter Q for global displacement and the small letter q for nodal displacement of the element. With distinction, I follow. I use capital Q for displacement of the node in domain. I use small q for displacement of the node in the element with distinction, I use the notations. Now, here what I understand, Q1 denotes the displacement of node 1 in the domain. Similarly, Q2 represents the displacement of the node 2 in the domain. Understand? Therefore, I can also understand Q1, Q2, Q3, Q4 and Q5. I say they are the global displacements. Global displacements. They are the nodal displacements in the domain. That is what we can understand. Okay. There are 5 global displacements. So these global displacements are denoted by a vector Q, capital Q, which consists of the global displacements Q1, Q2, Q3, Q4, Q5, which is a column matrix. We define this global displacement vector as the column matrix. Understand? Therefore, you can write this Q as the transpose of row matrix also. You can define Q as the transpose of row matrix also. Okay? Next. Now, if F1, F2, F3 and F4 are the forces, including F5, F1, F2, F3, F4 and F5 are the forces acting at the nodes 1, 2, 3, 4 and 5. These forces we can represent in the matrix form and name it global load vector. F denotes the global load vector, which is also a column matrix. How you write? Transpose of the row matrix. Transpose of the row matrix. Global load vector. Make correction. This is transpose of row matrix. Transpose of row matrix having the elements F1, F2, F3, F4 and F5. Global load vector. Understand? Now, that is what I have written here. Global load vector. It is transpose of row matrix. Understand? And global displacement vector Q I have defined here. So Q, it is the transpose of a row matrix. If there are n nodal displacements in the domain, then how do you write this Q? So Q is a column matrix having the elements Q1, Q2, Q3, Q4, Q5 and so on and so forth. It ends with Qn. Understand? Right. Now, in the same model, if we observe the node 1 is fixed in position because under the action of these forces, the point at node 1 cannot displace because it is fixed in position. Hence, the displacement Q1 equals to 0. This is the boundary condition. Displacement Q1 equals to 0. Okay, next. Element connectivity information. Element connectivity information. We discretize the domain into subdomains and we give numbering to all the nodes. Now the question is, what is the first node of the first element and what is the second node of the first element? See here, I take an example and explain. I take a bar like this again. A bar of uniform cross section. Okay. It is supporting a tensile force like this. Now, I discretize the domain. What is the domain here? Bar of the body of the bar. Now, I discretize this into several subdomains like this. Okay. Now, this is a node, this is another node, third, fourth, fifth and sixth. This node, how you give numbering? This is numbered say 1, this is numbered say 2, this is numbered say 3. If you give, say 5 to this, and this becomes 4, this becomes 6. This is element 1, this is element 2, this is element 3, this is element 4 and this is element 5. Now, for first element, node 1 is the first node and node 2 is the second node. For second element, node 2 is the first node and node 3 is the second node. Next. For fourth element, node 5 is the first node and node 4 is the second node. All this information is given by a table. What is called element connectivity table. This element connectivity table gives node numbers of the elements. We say local node numbers. Element connectivity table gives local node numbers. We say node numbers of the elements. The corresponding node numbers on the body are called as global node numbers on the body and on the domain. The corresponding node numbers on the domain are called as global node numbers. Understand? Therefore, what we can understand? The connectivity establishes the local global correspondence. Right? Now, I follow a convention. If E denotes the element number, the first node is represented by E, the second node is represented by E plus 1. This convention I follow. This convention I follow. For example, this is the element. Element number is E. Element number is encircled. If first node is denoted by E, the second node is denoted by E plus 1. So this convention I follow. According to this, you can see, you can visualize here the node numbering. This is element 1. First node, second. Right? Element 2. Therefore, what is first node? 2. What is second node? 3. Element, this is how I follow, this convention. Okay? Now, capital Q1, capital Q2, capital Q3 and so on and so forth, they represent the global displacements at the nodes. Right? Global displacements at the nodes. Now, instead of taking all the elements of the domain, I take only one element. I take only one element. That I see. I take only one element. Connecting nodes 1 and 2. Then, so what is the displacement of node 1? I say Q1, small Q1. As I said, I use small letter Q to denote nodal displacement of the element. Because I am taking, this is the convention. This is the convention. Don't get confused. When I take element, the nodal displacements of the element are denoted by with small q's with corresponding subscripts Q1 and Q2. When the same nodal displacements are taken on the domain, I use capital Q's with corresponding subscripts. That's all. Okay. Now, we have an element here. Right? This element connects two nodes. If E equals to 1, for first element, tell me what is first node? 1. What is second node? 2. The displacement of node 1 is say Q1. The displacement of node 1 is say Q1. the displacement of node 2 is say q2. Then the element displacement vector q you can define as a column matrix with q1 and q2 as the elements. Therefore, what is q here? It is a column matrix. It is a column matrix having the elements q1 and q2. Okay, we name it element displacement vector. This is the element connectivity table. So how you prepare the element connectivity table? As I said, element connectivity table gives the node numbers of the elements and element numbers also. Next, node numbers of the domain, we say global numbers. Node numbers of the elements are the local numbers. Local numbers. Now, element number we observe here, and first and second nodes of the element we observe here. Now, when E equals to 1, we have first element. For first element, what is first node? Node 1. What is second node? Node 2. Understand? Next, when E equals to 2, that is for second element, what is first node? Node 2. What is second node? Node 3. Hence, these numbers represent the local numbers and these numbers represent the global numbers. Similarly, for element 3, first node is 3, second node is 4. For element 4, first node is 4, second node is 5. These are all the global numbers. These are the local numbers. Okay. Now, strain displacement matrix we derive now. Strain displacement matrix. Again we consider a one-dimensional element which connects two nodes, node 1 and node 2. Node 1 has the displacement q1. See here. And node 2 has the displacement q2. It has the displacement q2. Okay. Q1 and Q2 are the nodal displacements. They are the field variables at the nodes. Okay? Now, if U is the unknown displacement, I take a point P here. Say point P. Its displacement is unknown. Its displacement is say P. If U is the unknown displacement at any point on the element. Okay? Any point on the one-dimensional element. U equals to Q1 at node 1. Understand? U equals to Q1 at node 1. And U equals to Q2 at node 2. That is what I have written here. Okay, if U is the unknown displacement at any point on the element, at any point on the one-dimensional element, U equals to Q1 at node 1 and U equals to Q2 at node 2. Therefore, the unknown displacement field U we can write as N1 Q1 plus N2 Q2. What are N1 and N2? They are the shape functions. N1 and N2 are the shape functions. What are Q1 and Q2? They are the nodal displacements of the element. We know that N1 is a shape function defined in terms of J. We already derived the shape functions N1 and N2. Therefore, you know that N1 equals to 1 minus J by 2 and N2 equals to 1 plus J by 2. What is J? It is the natural coordinate. The value of this J equals to minus 1 at node 1 and value of this j equals to plus 1 at node 2. As j varies from minus 1 to plus 1, the length of the element is covered. Understand? Okay. Where n1 and n2 are known as shape functions, which is denoted by n. The matrix is denoted by n. Shape function matrix, it is a row matrix. It is a row matrix. Therefore, this expression we can write in matrix form. How you write? This equals to a row matrix having the elements n1 and n2 into a column matrix having the elements q1 and q2. Understand? In simplest form, you can write this U as n into q. N is the shape function matrix and q is the element displacement vector. What is q? Element displacement vector. It is a column matrix. What is the shape function matrix? It is a row matrix. We know what is shape function. Shape function is an approximating function, or you can say an interpolating function. Understand? Right? It is the function used to interpolate the nodal field variables. What are the nodal field variables? q1 and q2. With the unknown field variable, what it is? U. Shape function is an approximating function or an interpolating function used to interpolate nodal field variables with unknown field variable. Therefore, here using shape functions, u, q1 and q2, right, are related together. U equals n1 q1 plus n2 q2. How you write U? As n into q. N is the shape function matrix. This is the shape function matrix. What is q? Element displacement vector. Understand? Now, this is one-dimensional element. Okay? To define the geometry of this element, how many coordinates you want? You want only one coordinate, that is x. This is a one-dimensional element. How many coordinates I want? Only one coordinate, that is x. If x is the coordinate axis like this with coordinate origin here, this is node 1 and this is node 2. Therefore, any point on this element is defined by the coordinate x. Hence, if same shape functions n1 and n2 are used to define the geometry of this element, if same shape functions n1 and n2 are used to define the geometry of this element, then the formulation, what is called isoparametric formulation. That is what we see here. If the same shape functions n1 and n2 are used to define the geometry of this one-dimensional element, we say the formulation isoparametric formulation. Hence, according to isoparametric formulation, what you can write? X equals to n1 x1 plus n2 x2. X equals to n1 x1 plus n2 x2. Understand carefully. Understand carefully. Now, this is a one-dimensional element connecting two nodes 1 and 2. Okay. At node 1 j equals to minus 1 and at node 2 j equals to plus 1. Right? Now, the node 1 is specified by the coordinate x1 with respect to the origin of the reference frame, and node 2 is specified by the coordinate x2. Understand? Now at node 1, j equals to minus 1. What is n1? n1 equals to 1 minus j by 2. Hence, put j equal to minus 1. Then what you get? n1 equal to 1. And at the same node, n2 equals to 1 plus j by 2. Hence, if you determine putting j equal to minus 1, n2 we get 0. Therefore, in this becomes 0. n1 is unity. Then x equal to x1. Correct. X equal to x1 for node 1. Okay. And similarly for node 2, x equals to x2. That also we check. At node 2, j equal to plus 1. When you put j equal to plus 1, n2 becomes 1 and n1 becomes 0. Put n1 0 here and n2 you put 1. Then x equals to x2. Yes for node 1. For S for node 2, x equals to x2. Therefore, this formulation is correct. This formulation what is called isoparametric formulation, which we can use to define geometry of the element. Okay. Now, we see, the conditions to be satisfied by the shape functions. These shape functions chosen should satisfy the following. What is first one? The first derivative of the shape function. The first derivative of the shape function must be finite within the element. Yes. Yes. These shape functions satisfy this condition. Now, when you take the first derivative of this shape function with respect to j, yes, you get a finite value. D by dj of n1. How much you get? Simply 1 by 2. 1 by 2 into simply d by dj of n1. You get, what you get? 1 by 2 into minus 1. The minus 1. It is a finite number. Okay. Similarly, d by dj of n2. That is the first derivative. How much you get? It is 1 by 2. It is a finite. Next one. Displacements must be continuous across the element boundary. When we use these shape functions, the displacements are continuous. That also we can check. Next. Rigid body motion should not introduce any stresses in the element. Okay. Now, the strain displacement relation. We know that the strain displacement relation is epsilon equals to du by dx. Yes, we know this. Epsilon equals to du by dx. Okay. Now, how you write this du by dx? We know that j equals to 2 into x minus x1 divided by length of the element minus 1. We know this relation. The natural coordinate j equals 2 into x minus x1 by L minus 1. Understand? So therefore, we can write this du by dx as, see here, epsilon equals to du by dj into dj by dx. Okay? This is the chain rule of differentiation. Epsilon equals to du by dj into dj by dx. This is the chain rule of differentiation. Now, du by dj, that we have to determine. And dj by dx, that also we have to determine. Let us see. dj by dx. dj by dx, which equals to, now tell me, it is simply 2 by L. It is simply 2 by L. What is L here? Length of the element, that is 2 by x2 minus x1. Therefore, dj by dx we have here 2 by x2 minus x1. Right? Now what we have determined? du by dj. But we know that u equals to n1 q1 plus n2 q. Okay? What is n1? 1 minus j by 2. And what is n2? 1 plus j by 2. Therefore, we write u equals 1 minus j by 2 into q1 plus 1 plus j by 2 into q2. Okay. Now differentiate u with respect to j. When you differentiate u with respect to j, what you get? Minus q1 plus q2 by 2. Understand? Minus q1 plus q2 by 2. Okay, now see here. Epsilon equals du by dj into dj by dx. We have dj by dx, that is 2 by L. Now, epsilon equals to 2 by L into du by dj. How much it is? Minus q1 plus q2 by 2. Therefore, 2 get cancelled with each other. Then what you get? 1 by L into minus q1 plus q2. These are write like this. Epsilon equals to 1 by L into a row matrix having the elements minus 1 and plus 1 into a column matrix having the elements q1 and q2. What is L here? x2 minus x1. Now, this I write as epsilon equal to some matrix B into, this you can replace by Q. What is Q here? Element displacement matrix. The matrix B, what is called? Strain displacement matrix or element displacement matrix. What is B here? B is simply 1 by L into a row matrix having the elements minus 1 and plus 1. What is B? 1 by L into a row matrix having the elements minus 1 and plus 1. Understand? So this is the strain displacement matrix. Okay. Now we observe a note here. Use of linear shape functions results in a constant B matrix and hence the strain within the element is constant. If we observe the strain epsilon, right? Epsilon equals B into Q. What is B here? It is a matrix having constants. 1 by x2 minus x1, it is constant. And the elements of this row are also constants. So when we use the linear shape functions n1 and n2, right, they result in a constant strain displacement matrix B. And ultimately, the strains within each element are constant. And ultimately, the strain within each element is constant. Okay? Right. Thank you. Thank you very much.